So, in this lecture we will discuss first the concept of the domain, limit, continuity and differentiability, and later on we will proceed to analytic functions and Cauchy-Riemann equation, etc. So, let us first review the few concepts which are needed in the sequence. So, let S be a non-empty set of complex number non-empty set of complex number, and suppose Z naught be an arbitrary point in S. Then the set of those points Z such that mod Z minus Z naught is equal to say delta, where delta is some positive real number, and let delta greater than or equal to 0 be a real number. Then this collection of the set this is denoted by basically some gamma, and we call it is a circle centered at Z naught and radius gamma and with radius delta. So, this is the equation. Similarly, when you say the set of those points Z such that Z minus Z naught is less than delta, then this collection we will denote the V x naught delta or sorry Z naught delta with the ball centered at Z naught with the radius delta, and it is an open disk. It is called the open disk centered at Z naught and with the radius delta. Okay. It's with the radius delta. Then closed disk, the set of those Z where Z minus Z naught is less than or equal to delta. This we denoted by say V Z naught delta, where it is the closed disk centered at Z naught and radius delta. So, these are then analysis we mean the set of those points, the set of those complex number Z such that R 1 less than mod Z minus Z naught less than R 2. Collection of all such point Z centered at Z naught which lies between the two concentric circles. This is one circle centered at Z naught with a radius say R 1. Here we have another circle which centered Z, same centered Z naught and radius R 2. So, these are two concentric circles. Then set of those points which lies in between these two circles is known as the annulus. And if these are open, means the boundary is not enclosed, then we call it is a open annulus. Otherwise, when the boundary is there, then R 1 less than or equal to Z minus Z naught less than or equal to R 2, then this will called a closed envelope, a closed annulus, closed and annulus. Okay. Now, the delta neighborhood of this is defined as, which is equal now delta neighborhood of a point Z naught. The delta neighborhood of the point Z naught, we denote this by n Z naught delta. N is the collection of those complex number Z such that mod Z minus Z naught is less than delta. It means we are taking all such point inside a ball centered at Z naught with a radius delta. Then this collection of such point we call it as a neighborhood or delta neighborhood of the point n. The interior point we mean of a set means a point z naught, a point z naught is an interior point of the set S, of the set S if all the points in some delta neighborhood of Z naught are in S, or in other words we say that is there exists some neighborhood of Z naught which is totally contained inside S. So, this is our S. A point Z naught is said to be an interior point of this set if we are able to get one neighborhood around a point Z naught with a positive radius set delta, however small this delta may be, but there exists some delta greater than 0, at least one delta we can find such that all the points inside this neighborhood are the point of S, that is this neighborhood is totally lies inside S, then we say Z naught is a interior point. And collection of all such interior points open set. What is the open set is? A set is said to be an open, a set is said to be an open set if every point of it is an interior point. Every point of it is an interior point. So, obviously, the exterior point we define as the set of those points which are not the interior point, or you can say a point Z naught is an exterior point of the set S if all the points in some neighborhood of Z naught, some delta neighborhood of Z naught are outside of S. So, suppose this is a point here, and if we are able to get one neighborhood around the point this which does not contain any point of S, then we say this point is an exterior point of S. So, like boundary point a point Z is a boundary point of S if every delta neighborhood of Z contains at least one point of S and as well as at least one point of its complement. Complements, that is not in S. So, a boundary point is the point. Here this point will be a boundary point, because if I draw any neighborhood around this point, then it will contain both the point of S as well as point outside of it. That is, at least one point is available here, which is inside S, another point which is outside it. So, such a point is said to be a boundary point. Okay. Now, closed set is a set is closed, a set S is said to be a closed set if every boundary point of S point of S belongs to it. Means if it contains all its boundary point, then all complement of the open sets, we also call it a closed sets. Okay, set is closed. So, a set is said to be closed when its a boundary point, all the boundary points are inside. The bounded set an open set S is said to be bounded if there exists some positive real number m real number m such that all the points of the sets is less than or equal to m in absolute value, that mod of z is less than or equal to m for all z belongs to S. If we are unable to get such m, then set is said to be unbounded. If no such m is possible, then set S is said to be unbounded. Means we are unable to get such an m for which this condition holds for all z, then such a set is said to be a unbounded set. Then connected set, an open set S is said to be connected if any 2 points Z1 and Z2, any 2 points Z1 and Z2 of S can be joined by means of a polygonal line which is totally contained inside S. The meaning is this: suppose we have this set, this is our set S. We said this set is connected, because if we pick up 2 points Z1 and Z2, suppose any arbitrary 2 point, then if I join this Z1 Z2 by the straight line directly, then entire line does not belongs to it, because there is a gap, there is a portion which lies outside of it. However, one can draw the polygonal lines like this. A polygonal curve means we are going from Z1 to here and then this. So, entire polygonal line lies totally inside S, then such a set is said to be a connected set. If we take this suppose I consider circle which is also a connected set, because take any arbitrary 2 point, one can always find the zigzag position which is totally linear, or maybe a straight line also one can go for it, but there may be a set which are not connected set. For example, suppose I take collection of these sets, set of all point S which belongs to this as well as this, union of this. Now, this set S is the union of these two, suppose. Okay. Then this set will not be a connected set, because as soon as you pick up any arbitrary point here or any point here, you are not able to get any polygonal curve which can connect these 2 points without leaving the set S. So, such a set is a disconnected set. Okay. These are the connected set. Okay. So, this meaning of this. Now, domain we define now. Domain, an open connected set is called a domain. So, domain is not simply a set, what it should be an open connected set, that is a collection of the points is said to be a domain when it is an open set, that every point is an interior point, and connected means if any two arbitrary point we picked up from the set, then one can able to draw a polygonal curve joining these 2 points which is totally concerned inside. Okay. And region, a region is a domain together with all or maybe some or maybe none of its boundary point. So, when the domain is combined with the elements of the boundary, either all or maybe some or maybe none, then this collection will call it the region. Now, for example, if we take this, suppose I say real part of Z is greater than 0, then real part of Z is greater than 0 means x, basically real part, if Z is x plus I y, then real part of Z is x, x is positive. So, this is our complex plane, this is x axis, this one is the y axis. Now, we want x to be greater than 0. So, the all the points which are falling here, this will be the collection of this point will give the set real part of Z is greater than 0. Now, obviously, this set is an open set, because the boundary is not included, and second one is also connected, one can join any 2 points. So, it is a domain. Example of it is an open connected set. However, if we take suppose another example, the set of those point where the real part of Z is not equal to 0, then in that case real part of Z is not equal to 0 means the x should not be 0, that is the set of all point x plus I y where the x should be different from 0. So, that is only possibility when you remove completely the imaginary line. If I remove this part, this is deleted, delete this part, imaginary line, that is by axis. if I derive completely by axis, then set of all points which are here as well as which are here, except this line, this is deleted. Okay. So, this forms a set. Is this connected set? No, it is not connected, because if we picked up here or if we picked up one point here and one point here, then in order to connect these 2 points you have to cross this line, but this line is not permitted, because the x should not be 0, because at this point x becomes 0. So, this set is not connected. Then will it be a region? Yes, it is a region, because it will region is a domain. So, it is not a domain at all, it is not an open connected set, but it is the collection of the points only, that is all. So, it is an open unbounded, you can say it is an open set, unbounded, not connected set, that is all. And since it is not connected, so it is not a domain, it is not a domain, while this one is it is an open connected set. Now, if we take this another example, says see, suppose I take the set of those points z where 0 less than argument of z less than pi by 4. What if this is the argument of z is 0, means this x axis, argument of z is pi by 4. So, this is angle pi by 4. We are taking those points which are lying between 0 and pi by 4. So, basically this is the same as this set of all x plus I y, where argument z is tan inverse by over x. So, tan inverse 0 is 0. So, we can get 0 less than equal to less than by less than x. This is the set. So, this by is equal to x is this line, because pi by 4, this is the pi by 4, and by is equal to x this line. So, we are getting only these points. By this line, these two lines are not added, this line is dropped, this line is also out. So, this set is a connected set, it is an open set. So, it will be a domain. Okay? That will be domain. Now, let us come to the functions. Of a complex variable. Z. Functions of a complex variable Z. So, let S is a set of complex numbers Z. S is the set of all complex numbers Z. A function f defined on S is a rule that assigns to every point z in S a complex number f of z. Okay. We denote this is it as w equal to f z, and z is a complex number, z is a x plus I y, then this mapping will also be a complex number, and we say it is u plus I b u x by plus I time b x by. So, if we have this z plane, here we have a w plane, this is x axis, this is y axis, this is real axis, this is imaginary, here is u axis, this is v axis. Then take any point here, say small z. Under this, a function f is signed, f is a rule which is signed the point z of capital S, this is our capital S, a set of point on which the function is well defined. Then find the value of z under f, then this f will give a point f of z in the w plane, okay, and this will be a complex quantity. Okay. For example, suppose I take f z is equal to say z square plus 3 z. This is our problem. Then z is x plus I y. So, if I substitute z equal to x plus I y and just open it, then what happens? W which is f z, this is equal to x plus I y whole square plus 3 x plus I y. So, separate out the real and imaginary parts. So, we are getting from here is that x square, then minus plus I square by square means minus y square plus 3 x, is it not? This will be u plus I v, I v will be equal to x square minus I plus 2 x by. So, 2 x by I times then plus 3 y. This is. So, basically this comes out to be u as a function of x by and plus v as a function of x by. So, this gives you a function. The domain of definition of the function f is the same as we define in case of real, that the set of those points where the function is well defined is said to be the domain of definitions. Okay. So, here we will take. Now, in case of this real, we are looking for the single variable case, single valued functions only, but in case of complex also we get a multivalued functions, multivalued function. So, we divide into single valued and multivalued function. So, what are the single valued function? Multi-valued functions. If for every z belonging to the domain of f, df I am writing domain of f or S, where the domain, there exists an unique image in the w plane, then the function f z is said to be single valued function. Otherwise, multiple, and if for z belongs to the domain f, we get more than one images. One image is in the w plane, then function f z is said to be multivalued function. Valued function. For example, f z is equal to say 3 z plus 1. This is a single valued function. Corresponding to each z, we get only one image. However, if we take the function f z at z raised to the power half, then for each z we have the two images. So, it is a multivalued function. Valued function. Okay. So, this will be examples we will see later on, those let me finish first. Then we introduce the concept of limits. The limit of a function of complex variables. So, let us see how to define the limit. Let f z be a single valued function, of z, of a complex point z defined on the set S, which includes the delta neighborhood of a point say z equal to z naught, of a point z equal to z naught. Okay. Now, we say z naught. Then the function f z is set to have a limit say L, which is also a point in a complex number, which complex number L, as z approaches to z naught, if for a given positive number epsilon r greater than 0, howsoever small may be, there exists, if for a given for a given epsilon r greater than 0, there exists a real number delta depends on epsilon r greater than 0, such that modulus of f z minus L less than epsilon r whenever 0 less than mod z minus z naught less than delta, where L is finite, limit finite, where and we write this this as limit of the function f z when z tends to z naught is L, where L is finite. Okay. Now, here if you look, we have taken the deleted neighborhood of z naught. So, here in case of the limit, when we say the function f z has a limit at z tends to z naught exists, then it is not necessary the function has to be defined at z naught. So, notice the function f z need not be defined at the point z naught. Still you can say the function f z has a limit L. Now, if this limit does not exist, now if no such L is possible, then we say the function does not have a limit. If no such L, which is in C exist, then we say that the function f z, then the function f z has no limit. So, basically this concept of the limit depends on the path of where the point is going. When we say this is our z space, z plane, here is W plane. So, suppose I take Z naught here and I take any arbitrary point Z in the neighborhood of Z naught. So, that Z may approach to Z naught in any way, either this way or maybe some, it is because it is in the neighborhood. Then corresponding images f of Z, if it goes to L in whatever the path you choose, if all the path is the function f z tends to L, then only we say limit of the function f z when z approaches to z not exist. If there exists at least one path where the limit differs from the another path, then limit will not exist. So, here this is something more complicated than the limit of a function of single variable, a real variable, because in case of the real we picked up the limit only either from the left hand side or from the right hand side, and then we say the limit of the f x when x tends to x naught is exist. But in this case, in all these sort of direction the approach path may be possible. You can choose any path which can approach the point z naught from any direction, in fact inside the circular disk centered at z naught with a suitable radius at delta. So, here while looking the limit, you should be careful that the limit from all the path should exist. But since there are infinite many paths, so how will you test the all the path and find the calculation? So, in order to avoid this thing, we use the epsilon or delta definition to confirm whether the limit exists or not. If this condition is satisfied, then it will give the guarantee that whatever the path you choose, the limit will always exist. Okay? Let us see the example. For example, let us say the function, say using epsilon or delta definition, so that the limit of this function z square minus z as z tends to minus I is I minus 1. Okay. So, let us apply epsilon delta. What the epsilon delta definition said, that for a given epsilon is known, we have to identify a delta which satisfies this condition. So, let epsilon is greater than 0 is given. This is given. Okay. We want to find delta which should depend on epsilon positive such that this condition must hold f z minus L, that is f z is what, z square minus z minus I minus 1, this is L, should less than epsilon provided or whenever this z 0 less than z minus z naught. Z minus z naught means z, this is the point tends to I, z naught is minus I. So, z minus z naught means this z plus I is less than delta. So, we have to identify delta. How to start with this? Consider this part mod z square minus z minus I minus 1. Consider this. Okay. Now, this will be equal to z square plus 1 and minus z plus I. Now, this is the same as z plus I, because z square plus 1 can be z plus I, z minus I. So, z minus I minus 1, is it not this mod. So, this is less than equal to mod of z plus I into mod of z minus I minus 1. But mod minus I minus, because we want I again. So, plus I, if I choose, then it becomes minus I minus 2 I, that will satisfy this condition. Now, this mod z plus I is again less than equal to, so z plus I, and this will be equal to less than equal to mod z plus I and plus mod 1 plus 2 I. Just apply the mod z 1 plus z 2 as mod z 1 plus mod z 2. Now, this is equal to mod z plus I and then within bracket mod z plus I, and what is this? Square root of this. So, under root of 5. Okay. Now, suppose for a given epsilon we are able to get delta, then we want mod z plus I should be less than delta. So, here we should write that this portion, this part is nothing but right hand side of this, part, this. So, it is less than equal to, if we choose this z plus delta I, mod z plus I plus root 5, which is basically less than equal to delta into delta plus root 5. If I take this to be less than epsilon, then entire thing is satisfied, that for this less than delta we are getting the difference is less than epsilon. So, what is this? If I solve this equation, and when you get, you will find the delta will come out to be less than under root epsilon plus 5 by 4 minus under root 5 by 2. Why? Because just a quadratic equation, delta square plus root 5 delta is less than epsilon. Make the perfect square by adding this term epsilon 5 by 4 whole square and so on, and then subtract it, we get this one. Okay. So, delta, it means for a given epsilon greater than 0, you have got the delta which is less than this value. So, if I choose this as a delta which depends on epsilon, then whole things is complete. So, this proves the, so for given epsilon greater than, we choose delta to be this number less than under root of this part, this number. Okay. Then set it. So, continue, limit exists, limit is I minus 1. Okay. So, this is the way, please check it. Okay. This is the way we can do it. Okay. Limit I minus 1, is this okay? Please check it again. Yes. But if it is asked whether this limit exists or not, or so that limit of this real part of z minus imaginary part of z whole square divided by mod z square, z tends to 0, so that limit does not exist. Now, here we need not to go for epsilon delta, we have to simply identify the path such that two paths along two different paths limit differs. So, what are the paths now? We wanted limit when z approaches to 0 from 0. Okay. So, I can choose any path. Suppose I take a point z, I take the first path, this one. So, case 1, first path is when it goes down, that is y tends to 0, x tends to 0 later. Second case, I can choose the path like this. This is our second case. This is second case. This is first path, this is second path. Second path is, say, x is tending to 0, y tends to 0, and third path may be any line, any curve you can say, or line y is equal to m x, y is equal to m x. So, I have taken this, there may be other path also, but if these three paths if I choose, suppose, and in all three the between any two paths the limit does not differs, then we say it is a limit does not exist. Okay. So, let us take this one. What is the function? Function f z is the function f z is real part of z minus imaginary part of z whole square divided by mod z square. That is, the function is real part of z is x, imaginary part of z is y, by x square plus y square. This is our function. So, we are interested in finding the limit. So, in the first case, what is the limit of this function? Limit when z approaches to 0. First, y tends to 0. So, when y is tending to 0, then what you get? X square by x square, limit comes out to be 1. You see here. Okay. In the second case, when x is 0, this is 0, this is 0, and again the limit comes out to be 1. So, along these two paths, limit is coming to be 1, but what about the third path? Third path, the limit of the function f z when z approaches to 0, this is the same as the limit, substitute y equal to m x. So, when z tends to 0 means, if I take x tends to 0, y tends to 0. So, here substitute, let x z tends to 0, putting y equal to m x. So, what we get? X minus m x whole square divide by x square m x square, and from here we get x square is cancelling, we get 1 minus m whole square over 1 plus m square. So, limit of this is coming to be this, but it depends on n, depends on m. So, it means if I change the slope of this line, if I change the slope of this line, say this line, then the limit along this line and this line differs, because it depends on m. Therefore, limit varies along various path. So, limit does not exist. So, limit does not exist. Limit varies along different path. Therefore, limit does not exist. Does not exist. Okay. So, that is what is this clear. Now, let us come to the continuity, a definition of the continuity. Continuity. A function f z, let f z be a single valued function, of z defined in some neighborhood of z naught, including the point z naught. Here the in case of continuity, it is must, the function must be defined at the point z naught. Then function f z is said to be continuous at a point z equal to z naught if for given epsilon greater than 0, however small may be, we can find a delta, a real number delta greater than 0, which depends on epsilon as well as the point, such that the mod of f z minus f z naught less than epsilon whenever mod of z minus z naught less than delta. That is, the meaning is this: when f is continuous, f z is continuous at a point z equal to z naught, means limit of this function f z when z tends to z naught exists and equal to the value of the function f z naught. So, in case of the continuity, 3 points is very important. First is the function must be defined at the point z naught. Second is the limit of the function f z must exist, and third is both should be identical. Now, if any one of the condition fails, the function will not be continuous at the point z naught. So, what are the possibility is for the continuity this one. Okay. So, if anyone else, so we get for continuity 3 things are essential. Continuity, number 1, the function f z is to be defined, is well defined at the point z naught. Second is limit of the function f z when z approaches to z naught must exist, and third is both should be equal, and third part is that both should be equal. Limit third is the condition A is satisfied. Third is limit f z must be equal to f z naught when z tends to z naught. So, third condition. So, if suppose first two satisfied, but the third does not satisfy, then the point is said to be a removable discontinuity point. For example, if we take the function sin z by z and suppose I take the function f z sin z by z when z is not equal to 0 and 0 if z is 0. Then the limit of this function f z when z tends to 0. Okay. Now, if I take limit of this function when sin z by z when z tends to 0, what will be the limit? This is cos z and this 1, is it not? But it differs from the value of the function at the point 0. So, the function has a discontinuity at 0, but this is known as the removable discontinuity. Why removable? Because we can redefine the function as capital F z equal to small f z when z is not equal to 0 and equal to 1 if z equal to 0. Then this function becomes continuous, and that is why. Now, another results also note, if the function f is continuous, at a point z naught which is x naught plus I by naught, then its real and imaginary part, parts will also be continuous. Okay, and that is all. Thank you very much. Thanks.